Hello! Quantum entanglement is one of the most striking and non-intuitive features of quantum mechanics. When two qubits are entangled, a measurement of one seems to instantly determine the state of the other one, even if they are light years apart.
Stop! What? Spooky action at a distance? Impossible. Nature does not play dice. How could you possibly go faster than the speed of light? This is nonsense.
In 1935, Einstein, along with Podolsky and Rosen, challenged this exact idea in what became the famous EPR paradox. They believed that quantum mechanics, as it stood, was incomplete and that hidden variables must exist to preserve locality and determinism. But modern experiments, especially those testing Bell's inequality, have confirmed it beyond doubt. Entanglement is real, non-local, and profoundly quantum. Einstein's intuition was brilliant, but on this point, the data disagreed. The result? A universe stranger than Einstein imagined, but astonishingly accurate. Let's pose the fundamental question. Can quantum entanglement be used to send messages faster than light? It seems tempting. After all, if Alice and Bob each hold one half of an entangled pair, and Alice measures her qubits, Bob's qubit instantly changes. Could Bob interpret that change and decode a message? To explore this idea, let's imagine the following setup. Two observers, Alice and Bob, placed at opposite ends of the universe. Each receives one particle from an entangled pair. The qubits are created in a controlled source and then sent in opposite direction at nearly the speed of light. Once they far apart enough, let's say 100 light years from each other, each observer will perform independent measurements on their particle. The key? Alice chooses when to measure her qubits. Does that instantaneously affect Bob's results? We are not just asking whether the qubits remain correlated. That's already well known and established. We're asking this question. Can Bob detect any change before receiving any classical signal from Alice? In other words, can he infer Alice's action instantly using only his measurement outcomes?
So now we're gonna prove mathematically the no communication theorem. So what are the Bell states? The Bell states are entangled states, which the four standards are given here, and those states are maximally entangled, meaning that the two qubits are perfectly correlated, no matter how far apart they are. So if qubit 1 equals to 0, qubit 2 equals to 0, and similarly, if one qubit equals to 1, the other one equals to 1. Or in this case, for example, if one qubit equals to 0, the other one is equal to 1, then the other one, if it's equal to 1, is equal to 0. Those states are not separable. We cannot express the state by the expression of one qubit or the other. This is the only way we can express it. In this demonstration, we're gonna use this first one, 1 over square root of 2 of ket 0, 0 plus ket 1, 1. Now we go to the second step. We're gonna construct the density matrix. The density matrix for a pure quantum state is given here by this ket of the state, tensor product of bra of the state. Let's calculate it. Phi AB, our density matrix for our state here. So we're gonna get this expression. By developing it, we see that we get ket 0, 0, bra 0, 0, ket 0, 0, bra 1, 1, and so on. And at the end, we're gonna get this expression right here, 1 over square root of 2 of this matrix. So each of those calculations is gonna result in a 4x4 matrix with all zeros except for one of the corners. So let's show the example for one of the matrix. So this first term right here, ket 0, 0, tensor product of bra 0, 0, is going to be developed into this. Ket 0, bra 0, tensor product ket 0, bra 0. Ket 0, bra 0 gives us 1, 0, 0, 0. And by further developing it, we'll get an all zero matrix except for one of the corners. We're going to combine all of them and get Phi AB, the density matrix, to 1 over square root of 2 with 1 only on the corners. Now we're going to calculate the reduced density matrix. So we want to understand Bob's state alone. So we're going to take the partial trace over Alice's qubit. This is like ignoring Alice's system and focusing only on Bob's. So mathematically, the reduced density matrix is given us here. Phi B equals to the trace, partial trace over Alice of Phi AB of the full density matrix, which is given here by this expression. So let's compute this step by step. For I equals to 0, the first value of Alice's qubit, gonna get all this by developing. Let's calculate the component. So when we calculate the component, we're gonna get this expression here. And we can see that after developing it, all of the terms where bra0 get 1 appears are going to be equals to 0, since this expression equals to 0. So we can simplify into these 4, which by the end we're going to obtain 1, 0, 0, 0. Of course, we cannot forget the 1 over square root of 2, which comes from here. Now let's take the other value for Alice's qubit, which is 1. Similarly, we're going to calculate it, and many terms here are going to vanish because bra1 gets 0 equals to 0. By the end, we're going to be left out with this expression here, 0, 0, 0, 1. Now, we're going to combine this, and we're going to combine the results into this. And the reduced density matrix of Bob is going to be equals to 1 over square root of 2 of 1, 0, 0, 0 plus 1 over square root of 2 of 0, 0, 0, 1, which by the end is going to give us 1 over square root of 2 of 1, 0, 0, 1. Here we recognize the identity matrix. So by the end we get 1 over square root of 2 of I, or y over 2. But what does this tell us? We get that the reduced density matrix for Bob is equals to 1 over square root of 2 of I, which is the maximally mixed state, meaning that this state is completely random. So Bob's qubit alone is totally random, no matter what Alice does on her qubit, which proves that no information can be sent from Alice to Bob by measuring or manipulating Alice's qubit only, since Bob's state is still completely random. So even though they share an entangled state with perfect correlations, we cannot send any information since Bob's qubit is in totally random state, no matter what Alice does on her qubit.
Alright, so now let's use MPQP and realize a little experiment. Let's say Bob and Alice are two good friends, and Bob will ask Alice a simple yes or no question, but she needs some time to think about the answer. And in that time she travels very far away, even to the moon. But luckily, obviously, since they are good friends, they have an entangled pair of qubits between them. Before leaving, Alice tells something to Bob. If you measure your qubit with 0, the answer will be yes. And if you measure your qubit with 1, the answer is no. So now let's actually see with MPQP could they use entanglement to communicate faster than light. Let's test this idea. First of all, we will try to prove that the entanglement actually works with MPQP. We start by creating an entangled state called an EPR state, and it looks like this. This means that if one qubit is 0, the other is also 0, and if one qubit is 1, the other is also 1. We simulate this by measuring both qubits repeatedly. Here is our code. And let's try it. We only get ket 0, 0 or ket 1, 1. Never ket 0, 1 and never ket 1, 0. So the two qubits are always correlated. So yes, the entanglement works. Knowing the value of one qubit instantly tells us the value of the other. But now comes this question, can Alice control what Bob will get? Let's do a second experiment. This time Alice tries to send a message by measuring her qubit. Alice wants to send the answer yes to Bob. To do that, she simply measures her qubits. We will make this simulation. We let Alice measure her qubits and then Bob will measure it as well. And what about the results? Alice's result is completely random actually, because sometimes she will get 0, sometimes she will get 1. And because of that, Bob's result is also random, sometimes 0, sometimes 1. Alice cannot control her outcome, so she cannot control Bob either. So this is the core idea of the no communication theorem. Even if they share entangled qubits, Alice can't use them to send a message to Bob. The entanglement creates a correlation, not causation. But now that they are so far away, Bob won't give up. He definitely wants to get the answer of this question. So let's get into a last experiment. What if Bob tries a trick? Bob wonders, even if I can't read Alice's bit directly, maybe I can detect whether she measures her qubit or not. Why would he think that? Well, in quantum mechanics, if a system is in superposition, we can sometimes detect it by interference, like in a double slit experiment. So here's the idea. If Alice doesn't measure, the system remains entangled in superposition. And if Alice makes a measurement, the state will collapse and there's no more superposition, right? So maybe Bob can use this to tell whether Alice has measured or not. That will let her send a bit of information. For example, I measure will be equal to 1 and I didn't measure will be equal to 0. Will that work? Let's test it.
So here is the final experiment. Bob will try to detect superposition via interference. We'll run two versions of the experiment. In the first case, Alice doesn't measure at all. Bob will apply Adamar gates and he will measure his qubit. The results, we see interference. Bob gets a mix of 0 and 1. Now let's try the case B. Alice does measure and the state will collapse. And here is the results. There's no interference anymore. So Bob will always get the same results. So it worked, right? Well, that's a fast. Because actually, here's the problem. For Bob to detect the difference between superposition and the collapse state, as you can see in the algorithm, he needs to interact with both qubits. But Alice's qubit is on the moon, isn't it? So although the physics change, Bob can't detect that change locally, and the interference experiment requires both qubits to be together. So what did we learn? The entanglement creates a strong and non-classical correlation, but unfortunately those correlations can't be used to transmit information. Alice's choices will only affect Bob's results when they're compared later via classical communication. So the no communication theorem ensures that causality and relativity remain safe.
Unfortunately, my friend Bob, you can't get the answer instantly. You will just have to wait for Alice's message, the old-fashioned way.
So, now let's talk about applications and implication of quantum entanglement and why this actually matters for us. First, entanglement reserves special relativity. Even though it looks like qubits influence each other instantly, natural information travels faster than light. So there is no violation of Einstein causality, no superluminal messaging. Second, it's the foundation of quantum teleportation. Thanks to entanglement, we can transfer the state of a quantum system from one place to another without moving the qubit itself and still remain within the limit of physics. Third, entanglement is crucial in CHSH games. These are experiments designed to test Bell's theorem and entangled qubits that quantum strategies beats classical ones, showing that quantum reality is fundamentally non-local. Finally, it secures quantum communication. In protocols like BB84 or E91, entanglement guarantees that any eavesdropping would break the quantum correlation, so it's detectable immediately. That's what makes quantum cryptography probably secure. So in short, entanglement may feel like magic, but it respects relativity, and it's already powering the future of secure communication and quantum computing.
So did Bob ever get his answer? Well, yes, but definitely not instantly. Let's recap. Entanglement is strange. It links qubits across the universe in a way that feels like magic. But it's not the kind of magic that lets you send secret Morse code from the moon. We saw through our experiment that no matter what Alice does with her qubits, the Bob's qubits remains completely random unless they use a classical communication channel. This is the essence of the no communication theorem. You can share entanglement, but not information, unless you pick up the phone. It's as if nature gave us a quantum teleportation but then said, "Cool trick, but don't forget to text afterwards." So entanglement is powerful, but not a loophole to break the speed of light. Quantum mechanics, once again, stay consistent with Einstein relativity, and Bob is still waiting for Alice's message. Thanks for watching.